Welcome back, everyone, to another session of this webinar series on scientific machine learning. I'm very excited to kickstart a new series today on machine learning meets information theory and statistical mechanics. This session is the first webinar in the 5-part series, and today we have an exciting speaker. We have Alemi from Google Research, who will be introduced by our session chair. And today I'm very glad to have as our session chair, Professor Max Welling, who's a research chair in machine learning at the University of Amsterdam and a VP of technologies at Qualcomm. He also has a secondary appointment as a senior fellow at the Canadian Institute for Advanced Research. He's a co-founder of Cypher BV, a university spin-off in deep learning, which got acquired by Qualcomm in 2017. And prior to that, he received his PhD in '98 under the supervision of Nobel laureate Professor Hoft. And Max serves on the board of the NIPS Foundation, now NeurIPS, since 2015, and has been program chair and general chair of NIPS in 2013 and 2014, respectively. So Max, Venkat and I are honored and pleased to have you with us, chairing this session. Please take it away and introduce Alex.
Yeah, so thank you very much for inviting me to be the chair of this this session. It's a new concept to me, but it looks extremely interesting to do something like this. So I'm going to experience it. Yeah, so I'm going to introduce Alex Alemi. So Alex is a chaste physicist like myself, and actually many other people in the field, now applying machine learning to sort of applying machine learning and intuition from physics, I think, to interesting problems. So currently, Alex works as a senior research scientist at Google, and he has been educated his bachelor was at the California Institute of Technology, and he did both his master's and his PhD at Cornell, also in physics. So I think I first met Alex, but he will have to correct me if I'm wrong, at a lunch that we had in Long Beach, maybe what that it was. I seem to remember that or not, but anyway. But you were talking about, it was with Kevin Murphy as well. And it was, yeah, you remember this was, I think it was SciML or something.
Yeah.
But you had been talking about, I think, the topic that you will be talking about today, which is basically a grand unified theory, which puts both graphical models as well as information theory, as well as statistical mechanics, basically in one big grand unified theory. I was super impressed by it then, and I'm still very impressed by all the work you've been doing since then, and I'm looking forward a lot to your talk and to a discussion afterwards. So please take it away.
Oh wow! So I mean, thank you so much, Max. I mean, I know that your job is to kind of say nice things about me, but I'm flattered all the same. So thank you.
It was intention. Yeah. It was meant. It was not just.
That's fantastic. Yeah. Wow. All right. So, hi everyone. I'm Alex Alemi. I work at Google as a research scientist, and yeah, today I want to kind of spin a tale, right? I want to take you on a journey. I want to try to connect some dots, kind of maybe talk about things that you have some familiarity with, probably in a way that you're unfamiliar with. Try to make some connections, give you a new way of thinking about some of the things that you have been thinking about. It's the kind of way that I think about these things these days, and it sort of drives most of my research. Hopefully I'll be able to make it through and introduce some of the things I've personally worked on, really sort of lay a groundwork for Pratik sort of next week to extend on a lot of these things and get into some more of the details. And hopefully we have time at the end to do some code and kind of show an example of how these things work. So at its core, I feel like, machine learning is about asking this question, right? How ought we model data? And I guess for this audience, I feel like there's a good, we can get a lot of guidance if we, by the answer to a different question. How ought we model a physical system? Because this is a question that I think we've had a lot of experience with. And so that's what I'm going to try to do. I'm going to try to convince you that the same way that we ought to think about modeling physical systems, kind of thermodynamics from an information theoretic perspective, is the right way. And that furthermore, that same way of thinking about problems in machine learning can help you invent sort of most of machine learning that has been done, and really give you a kind of a way to think about things. So that's the kind of plan. We'll see how this goes. But to start, I need to talk about thermodynamics, and I'm hoping people have some familiarity, but I'm going to try to talk about it in a way that is maybe distinct from the way that you were taught it in school. In particular, I want to focus on an information theoretic or a probabilistic perspective for thermodynamics. And this, I'm going to be cribbing, I'm going to be stealing from, the great E.T. Jaynes. If you haven't read his papers, Information Theory and Statistical Mechanics, I cannot recommend them enough. Really sort of fantastic. And at the time, remarkable, like new way of thinking about statistical mechanics from an information theoretic perspective. So I'm going to try to kind of build that story now for you. How do we do it? We want to talk about a physical system. In order to talk about a physical system, we need to start with sort of states. We need to start with a complete description of the system. We need to enumerate exactly the configuration of the system if we're going to talk about it. And that's what the state is. The state is just an exact configuration, an exact specification of what the system's doing. As examples, right? If we wanted to talk about a classical ideal gas, there's an Avogadro number of particles in a box, but each one of those particles, if it's classical, if you give me its position and its momenta, then, I know physics, I know classical mechanics, I could in principle sort of integrate the equations forward, and I could tell you exactly what the system is going to do. So the complete state of the system is writing down all of those Avogadro number of positions and momenta. For something like the Ising model, which you may be familiar with. If you're not, it's a simple model of sort of like magnets and stuff. Imagine a checkerboard, and each site on the checkerboard is a square that could be either black or white. It has a coin that's heads or tails, on or off, 0 or 1. In order to specify a state for the system, I need to tell you each one of those sites on the checkerboard, whether they're on or off, heads or tails, 0 or 1. Here I'm showing a picture of 128 by 128, some 50,000 or so sites. And for each one of those sites, I've covered them black or white. This is one state that the system could be in, right? It's one of many. There's lots of states the system could be in. Here's another state that the system could be in. It's just as valid a list of 50,000 Booleans as the other one. It's another configuration for this particular kind of model system. Here's another one, looks sort of clustered and things. And for the current audience, here's one that, sort of shows a lot of structure. But still, these are all valid configurations for the same model system, 128 by 128 Ising lattice. Another kind of system that we can talk about is a neural network. And really, you should, you hopefully have some familiarity. Neural network is, sort of a black box. It's got a lot of knobs. It's got a lot of parameters. It's got a checkpoint, right? Some bytes on disk that when read, tell the network how to behave, how to connect its inputs to its outputs. But you think of it as just a function. You should think of it as a function with a lot of knobs, a lot of things that can be tuned. And the state of the neural network is the setting of all of those knobs, the configuration, the checkpoint, the bytes that you have on disk that specify precisely what the rules are connecting the input and the output. So here I'm visualizing one of them, right? So this is a neural network that I designed to be a one-dimensional function. It has a one-dimensional input, just some X value. It goes through several layers, goes through 100,000 parameters or so, and spits out a one-dimensional answer. We can visualize that one-dimensional function with a graph. And here's the graph corresponding to one configuration of the neural network where I randomly set all the bits in the checkpoint. Both for this talk and life in general, I think you should think about neural networks as just being sort of function approximators, but not just function approximators. They have two very useful properties. They're expressive and they're sort of tunable. So by expressive, what I mean is that same like box, if I just randomly reset the bits, I can express a whole lot of other functions. So the same neural network that I showed before, I just change the checkpoint, I reshuffle it, I randomize it, I get all of these different functions out. But not just that. The neural network isn't just a way of making random functions. The sort of remarkable aspect about neural networks is that they're expressive. We can not just express lots of functions. We more or less can express all functions, and we can find those functions. So here I'm showing cosine of x, except it's not actually cosine of x. This is the same neural network. It's the same neural network. I just happen to be able to find, and generally for neural networks, you can efficiently find how to set the parameters of the neural network, how to adjust all the knobs, how to tune the knobs to achieve a desired outcome. So this is the exact same neural network that can express a function, which is like visually indistinguishable from cosine of x, and I can find it efficiently with with optimization techniques like gradient descent. And I can do this for basically any function I can imagine. Here, I'm trying to, be inventive and write down some function I dreamed up that seemed, analytically difficult, right? Some piecewise function with a sine squared or whatever, but it doesn't matter. The neural network can just as easily find this function as it could find cosine of x, as it could find basically anything I could draw. So for this talk and in life, you should think about neural networks as being rich, expressive, and tunable function approximators. To zeroth order, you should treat them as being able to express any function, and the useful property is that you can search in the space of all functions. They allow for efficient search. Okay, but eventually we'll talk about these as just other physical systems that we can adjust and talk about and reason about, just like we could the other kind of physical systems. Last one I want to talk about to try to make it easy and try to plot some things is a simple one. So imagine just a ball on a spring. Here, the state of the system, what's the configuration? It's a real number. It's specifying where on the string the ball is. Once I tell you that, I've sort of told you everything you need to know about this ball on the spring. Okay, those are states. States are complete description of the system. For some of these systems, that's hard itself to write down. For the ideal gas, I don't have a notebook that I can write an Avogadro number of position and momentas in. And honestly, I don't care, right? I very rarely actually care about the precise configuration that a system is in. There's only a finite set of questions that I'm interested in asking about it. And those are the state functions. There are things that I might be interested in. There are functions of the state that I might compute. There are things that in principle, if I knew the exact configuration of the system, I could compute a thing of interest. These are the kind of classic extensive variables in thermodynamics that we care about: energy, volume, number of particle, length of a wire, area of a surface bubble, the loss of a neural network, right? You give me the checkpoint, I could compute the loss. These are things that I could compute if I knew the exact configuration of the system, and often the things that I actually care about, not the configuration itself. Here's some examples for our ball on the spring. We said it had a quadratic energy. I might be interested in the energy. You tell me where the ball is, I tell you what the energy is, right? That's the state function. It's a function of the state. For the icing model, we could also compute the energy if we do the Hamiltonian, but there's other things I might be interested in, like how black or white is the picture, right? I could just sum up all of the pixels. I could measure the excess, or the, how black versus white is it, the magnetization of this thing by just summing up the state. You give me the state, I write a function, I calculate the sum, I give you that number. The thing I actually care about, less so the precise configuration. Okay. The problem is, for some systems that are sufficiently complicated, even writing down the state is itself complicated or impossible for something like the ideal gas. And so what we're going to do is, like I said, I don't care what configuration the system is in. We're actually going to make the problem a lot harder, because I'm not going to talk about what configuration the system is in. I'm going to try to talk about my belief about what configuration the system is in. This is a massively larger mathematical object, right? The configuration itself was already a complete description of the system. My belief about what the configuration the system is in is a thing defined on the space of all possible configurations of the system, right? It's a probability distribution on the space of all possible states. This is a ridiculously massive object. For something like the icing model, if you had 50,000 or so spins, if you had n spins, how many possible configurations are there? 2 to the n, an exponential number of configurations. And in order to properly express my belief about which configuration the system is in, I would need to give you a probability, right? Something that sums to 1 over an exponential number of those configurations, right? I have to say, oh, there's like 0.1% chance is this, and 13% chance is this, and I have to do that for all of the exponential number of things. This is a massive object. It's a big object, but what it allows me to do is express my belief, right? If I don't know which state the system is in, I can describe a sort of distribution. And even for something like the ball on the spring, it doesn't, how many numbers does it take to specify my belief in where the ball is? It actually takes an infinite number of numbers, because the ball on the spring was a real number position. In order to express my belief in where the ball is requires an infinite number of numbers. It requires a function, right? I need to specify any function I specify on the real line, if it's normalizable, is a valid belief I could hold about where the ball might be located. I could do things like, oh, I don't know where it is. It's somewhere around the middle, some kind of Gaussian or normal distribution. I might know where the ball is. I could express that belief. I might make it a very pointy, a very spiky, a delta function at position 2. I might say, I took a very precise measurement. I know the ball is there. That's valid in the space of all possible beliefs over the distribution of states. I could do anything I want, any kind of wacky function I could draw, weird disconnected things, whatever. Now what we're going to look for is some principles, some guidance that we could look for like, okay, we're talking about this thing. How do I decide sort of how I should set these beliefs? The first thing to talk about is how do we extend our notion of what we cared about to these distributions, right? I cared about the state functions. I cared about the energy or the volume or the length of the magnetization or the loss. How do I compute them now when I'm expressing my belief? Well, the natural thing is, those things were defined for a particular configuration. Now, if I'm talking about a distribution over configurations, I'll take the expectation, I'll take the mean, I'll take the average, right? That will take those state functions and allow me to compute them for any belief I have about what the system is in. And that should correspond to, if the system was in that distribution, the average value that I would observe from that distribution. The next thing is, okay, the kind of magic, the thing that we're going to take this problem, we made it ridiculous, we made it even more ridiculous. How are we going to get closure? How are we going to rein this thing in? We can adopt a principle. We can look for guidance. And in particular, I can say something that, I'm interested in setting my beliefs in how the system is configured to be simple. I am ignorant about most things in life. I don't know much about the structure of the system. And so I will look for some principle that allows me to express that ignorance, to really not say more than I have any right to say. I want the truth and nothing but the truth, nothing more, right? I don't want to say anything I'm not allowed to say. And the magic is Shannon and Boltzmann told us how to do this. If you have a distribution, if you have any beliefs that you have about the world, there's a way to actually quantify your ignorance. There's a way to quantify how expensive, how complicated, how expressive, how much it takes to write down your belief. And that's the entropy, right? The integral of P log P. This is a number. It's not defined on states. It's not defined for a configuration of system. It's a functional defined for your belief about the configuration of the system. If you give me your beliefs, you give me the distribution, I could calculate this quantity. And this quantity is a number that tells you sort of how complicated your belief is. Now, Shannon and Boltzmann, fantastic, very smart people, did make a little bit of a mistake in the sense that the entropy, as we all know and love, integral P log P, doesn't really extend for continuous distributions like our ball on a spring. The easiest way to kind of understand it is like the dimensions don't match, the units don't match up, right? This is supposed to be a number. We're trying to integrate over some volume, like whatever our state system configuration space is. A distribution is a distribution, right? Ordinarily, if it was just integral of theta P of theta, it has to integrate to 1. So a distribution has units of inverse volume. If a distribution has units of inverse volume, what's the units of a log of an inverse volume? I mean, I don't know. So there's an issue, but it's easy to fix. The fix is we just sort of have to be explicit, right? We have to recognize that when we talk about distributions in general, we should do this for discrete, but especially for continuous, we need to kind of choose a metric. We need to choose a measure. We need to specify what it means for how far apart two points in kind of configuration space are by choosing some base measure, some other distribution that we can measure things with respect to. Maybe another way to say it is, we can talk about how complicated beliefs are, but only with respect to or in reference to some other belief. We can say how much you move when you go from Q to P, if you updated your beliefs from Q to P. You have to specify some prior, you have to specify some base measure, something that you assign a 0 in terms of complexity, and then everything is measured with respect to that. So we've done it. We now have a way, you give me your beliefs and we can quantify how expensive it is. And what we could do is we could look for a principle by which, hey, have as cheap beliefs as you possibly can, right? The truth and nothing but the truth. And that's sort of exactly what we'll do. So to kind of show how this plays out, let's do a little example. Let's imagine our ball on a spring. We might be interested in the energy, say. So now what we're going to ask is like, okay, you give me your belief about where the ball is and we'll kind of work things out. We're interested in the energy, that's going to turn into the average energy. And we also have this other measure that we can measure, this KL divergence, this relative entropy, this cost, this entropy type thing. So we have to choose some base measure. Let's have to choose the 0 for our complexity. Let's imagine a Gaussian 0,1 for no good reason, except that's a good starting point. So if you said that your belief was this distribution, we could calculate the average energy of the ball, right? Sample from this thing, calculate the quadratic, average the whole thing. You get an average energy of 1. And what's the KL divergence? We're going to choose this as the prior 0. KL divergence of the thing to itself is 0. So you choose a belief, that's a point on this plane, or this two-dimensional axis. Change your beliefs. Oh, what if you thought it was exactly a 2? What do you do? Well, you could calculate the energy exactly. And what do we do about the KL? If you specify, how much information does it take to specify that the ball is at an exact location? If this is a real number, it takes an infinite number of bits, right? A real number is a big number. keeps going after the decimal point. It really takes a lot of, that's a complex description of the system. To give an exact configuration for a complicated system or even a real number takes a lot of information. So it's sort of way up there on the y-axis. But we can do this for any beliefs that you have. Here's that weird one that I drew before. Doesn't matter. I can calculate the average energy and I can calculate the KL divergence. It's just a point on this plane. I can do that for this disconnected thing. It's just another point on the plane. And I can do this, we could do this all day. Let's ask what happens if we imagine all possible beliefs that you could form, right? Take this distribution and start morphing it. What do? Well, you start morphing the average energy, you start morphing the KL, you start sort of filling this space. You keep going and you consider now, this ridiculous mathematical object, your belief in all possible configurations of the system. Consider the space of all possible beliefs you could have about the system and plot all of those on the plot. And what do they get? You fill the space. But importantly, you don't fill the space. There's an edge. There's a boundary. There are some beliefs that are sort of this thing doesn't go all the way to the axes. There's an edge. There's a frontier. The beliefs that you hold that live on the frontier are special. Those are the ones that for any given fixed energy are the ones that have the lowest KL, that have the maximum entropy, that are the most ignorant. There are beliefs you could hold about what the configuration the system is in that express nothing except that the system has some desired expectation. Those states are special. Those states are maximally ignorant. Those are the ones that we should aim for, that we should hold in our head, because those require that we don't write anything else down except the things that we know. How do we find them, right? In the space of all possible distributions, how do you find them? We have an objective now. We just described the procedure. You look in the space of all possible beliefs P for the belief P that minimizes this KL divergence. And you could do it as a constrained optimization problem. Let's say you fix the average energy to be 4. You could search in the space of all possible distributions with energy 4 and try to minimize the KL. And eventually you'll find that you can't go any lower. There is some minimum KL belief that has expectation 4. If you wanted a different point, you just choose a different average energy. You do it again, and you'll find at another point on the surface. And you can do that for all average energies, and you can pick out all points on the surface. The KL divergence is a magical function. The relative entropy is a magical function. It's convex in its arguments, which means that the surface is guaranteed to be convex. Convex surfaces we can describe in multiple ways. We don't have to describe it as the coordinates on the surface. We could describe it by the derivative of a point on the surface. Because if the curve is convex and you imagine this green bar moving along on the surface, it traces out all possible slopes, but it doesn't you don't see the same slope twice. So if I want, I could identify each point on the surface by its slope. And mathematically, right, we could do like a Gauss transformation, or we could do a Lagrange multiplier. We could add some beta to the expected energy. And now if I minimize this objective for any fixed beta, what I'm looking for is a point on the surface with a different slope. You should really just think about that as you choose a beta that's like taking this curve and rotating it some amount, and then just searching in the space of all possible distributions for the one. You search in this whole space for the one that achieves the minimum of that rotation. Choose a different beta, rotate the curve, do it again, poof, you hit a different point on the curve. You choose all betas, you hit all points on this curve. Those are the special distributions. Those are the unique distributions. Those are the maximally ignorant distributions. Those are the equilibrium distributions in thermodynamics. It seems like we had a ridiculous problem. We considered this ridiculous thing, the space of all possible beliefs over the system, of all possible configurations of the system. The magical thing is once we can identify that what we're solving is a simple sort of unconstrained optimization problem, we can give a solution. We can write down the answer implicitly. We can solve this equation. You can solve this equation if you do calculations, calculus of variations, and you can discover that the solutions that live on that curve have a form. And the form is they're Boltzmann distributions. These distributions, as you vary beta, are the ones that minimize this objective for all beta. That's just the answer. That's just, math, fact. These are the distributions that are maximally ignorant. These are the distributions that are, the truth and nothing but the truth. They take this form, an exponential of, the Lagrange multiplier times the thing you're interested in. Energy out front is the sort of prior, the prefactor, the thing that we use to kind of measure the space, the base measure. And then the whole thing has to be a distribution, so it has to integrate to 1. So you have to integrate it to 1. You put the integrator, you put the partition function downstairs. This thing integrates to 1. It's a probability distribution. It's the solution to this problem. If you had more than one constraint, doesn't matter. Like the math is the same. Everything kind of separates out, separation of kind of constraints, and you end up with a generalized Boltzmann distribution. That's thermodynamics. Thermodynamics is this principle. I'm trying to describe a physical system. I don't know how to describe it. I don't actually care. So I'm going to describe my belief about what the configuration of the system is, and I'm going to seek some principle. The principle is I don't want to write down much. I want to be ignorant. I want to say the truth, nothing but the truth. I'm only going to describe the things I care about. I'm only going to describe some fixed number of expectations. I do that. I really follow that principle to its end, and I discover that there are beliefs that I could hold in my head that are optimal in this sense, and that those optimal things form a surface. They found a boundary in the space of all possible beliefs I could form. Thermodynamics is just the study of that geometrical object, that surface, that thing at the edge, those special states that are maximally ignorant. In fact, here's a plaster cast that Maxwell made of a paper from Gibbs. Like, it's an actual plaster cast of a thermodynamic surface. Now, once you do this, once you identify that there's some convex geometrical object, you could study it. You could measure derivatives on it. You could move along it. You could reparameterize it. You could describe it all different ways. And in fact, undergraduate thermodynamics is really just the sadistic exercise of asking students to describe the same object, that plaster cast on the right, countless different ways, doing all different kinds of coordinate transformations, describing in terms of coordinates and derivatives and all that stuff. That's all thermodynamics is. It's this identification that if you really kind of adopt this principle of ignorance, things can be described as living on a convex total surface, and mathematically that has structure, and that structure is structure we can manipulate and we could use to try to answer our questions. That's thermodynamics. That's all it is. Lagrange transformations, the different energies, free energies, intensive variables, derivatives are just the derivatives, all of it. Thermodynamics is really just that idea. How do I describe a system? I say, I don't care about the configuration. I only care about certain values. I want to seek in the space of all possible beliefs I should hold for the ones that are maximally ignorant. I want to minimize the KL divergence given some kind of constraints. That's machine learning. I argue machine learning is the same thing, or you can adopt the same principle. How should you set your beliefs about what the world is, or what you think is true, or what you think the cosmological constant is? You should adopt the same principle. You should set your beliefs to be the ones that are maximally ignorant given constraints. In machine learning, those constraints take the form mostly of like configurational constraints, causal sort of constraints in how we think the variables relate to one another. But it's all the same thing. Let's work through an example. Let's try to talk about parameter inference. Let's imagine we're a scientist today. What do you do as a scientist? There's something you care about, right? You're going to go out in the world, you're going to collect some data, and there's something that you care about, some parameter. Like, let's say you're a cosmologist, you're going to be on the Planck team, you're going to build a satellite, you're going to point out in space, you're going to take pictures, and what you care about is the cosmological constant. You want to measure it. You want to form some belief about what the cosmological constant is. Our cast of characters is, you will take a bunch of pictures. Here, my turtle's a picture. And you're going to also have some belief about what the cosmological constant is. In the real world, there's a causal constraint. There's a thing that we have to satisfy. I don't get to set what the sky looks like, right? That's outside of my control. The data is outside of my control. So all I get to set is this conditional distribution. I get to set what my beliefs are about the cosmological constant after I observe the pictures in Planck. How do I decide? What principle do I use to guide my decision about what I should believe about the cosmological constant? Let's just do thermodynamics. Let's just do the exact same thing. Let's just look for the maximally ignorant way to describe my beliefs that are consistent with what I observed. In order to do that, we need a prior. We need something to measure with respect to. We need some measure of like maximal ignorance. We need some way to describe what I expect to happen, what I think isn't complicated. And so for that, I can tell a story. It's the perfect world that I imagine. If you told me what the cosmological constant is, I think as a scientist, I know something about what the way the world will work. I think I know something about what things will look like, right? If you give me the cosmological constant, I think I can simulate, because I know cosmology, I know lambda CDM, I know whatever. I think I can simulate the way the universe will evolve. And furthermore, I know my satellite. I know how it measures things. I know the errors that it makes. I think in principle, feel as though I understand, and it's not that complex for me in my own head right now. My current beliefs, my prior beliefs are that if you told me the cosmological constant, I could simulate the results from the Planck experiment. And so that's what we're going to set as our target. That's what we're going to set as the goal. And then what we're going to do is the same as before. We're going to project, we're going to try to form a set of beliefs tomorrow that are as close as possible to my beliefs today, consistent with the constraints that I observed what I observed. And so you do it. You minimize the KL divergence between my beliefs tomorrow and my beliefs yesterday, subject to the constraint that, the pictures that I take in Planck are the pictures that I saw in Planck. I don't get to control that. You do that, you solve this, you write out this KL, you separate it and split it into two terms. One term that kind of, you separate the variables, one that kind of works in data space, one that works on parameter space. You've got one term, this term, the likelihood, which is, a measure. If I believe something about what the cosmological constant is, I can simulate what my pictures ought to be look like, and I can measure how good I made a prediction. That's the likelihood. The other term that you get when you take this KL is a KL, a thing that itself is a KL. It's a measure of how complex my belief is, right? This is the KL divergence between my beliefs about the cosmological constant tomorrow and my beliefs about the cosmological constant today. I have some prior beliefs about what it is given the papers that I read. And just as we did with the ball, let's do an example. Okay, let's not talk about the cosmological constant. Let's talk about something simpler. I'm going to, measure 5 points, and I'm interested in what their mean is. They come from some distribution. I don't know what it is, but I want to form beliefs about what the mean of the distribution is. Okay, so what do I believe? What's my kind of prior beliefs? My prior beliefs is that the data itself, I need a model for it. Let's imagine it comes from a normal distribution with some mean, theta, that I don't know. What's my belief about theta? I don't know. I need to set a prior. Let's call it a normal 0, 1 because I don't care. What's the data? Let's say I measure it. This is the data. I don't get to choose. And the thing I get to choose is what my belief is tomorrow about what the mean is. And let's do that. Let's do it just like the ball. I'm going to make a diagram. There's going to be 2 axes, one of which is this expectation, the energy that I get, the likelihood that I get if I had any belief about what the mean is, an expectation of the likelihoods over that distribution of beliefs about the mean. And the other one is this KL, how complicated that belief is. And I can do this for any distribution. So let me start. Here's some Gaussian thing. I can calculate the average energy. I can calculate the KL. The KL was 0 because that was my kind of prior, 0, 1. It lives right there. I could, let's say I tomorrow want to believe that it's uniform between -1 and 1. How much does that sort of cost me? Where does it live in the space? I calculate its energy. I calculate its KL. It lives right there. Boop. Do a different distribution. What if I measured 5 things? What if it's kind of close to one of those 5 things? I form a little mixture thing or something. Calculate these 2 numbers. Boop. Lives right there. This one lives right there. Let's fill the space. Fill the space, it fills the space, except importantly, it doesn't fill the space. There's an edge. There are beliefs that are optimal. There are beliefs that are maximally ignorant. There are ones that live on the edge. And the ones that live on the edge look like this. They're just certain beliefs that happen to be Pareto optimal, that cost the least to write down, that are the simplest ones that are consistent with the data that we observe. And they sort of, as we move along this curve, we trade off between doing a good job of fitting those 5 points because I concentrate closer on the mean that I observed at the 5 points, and doing a better job of matching my beliefs yesterday, things that look closer to the prior. And as I slide along the surface, I trade off between those 2 things. This edge. I want to live on the edge. There's no reason not to live on the edge. The edge dominates over the bulk. And we can characterize what those things are. We can solve the equation. We know the calculus of variations. You know what the answer is, and the answer takes the form of a Boltzmann distribution. The way that we wrote this is an exponential of a log. You take the exponential of a log, you get the thing itself. You notice this might look familiar. P of theta given d is q of theta, q of d given theta. If beta equals 1, this is the Bayesian posterior. We have just reinvented Bayesian inference as a form of thermodynamic reasoning about what my belief should be about what the parameter that governs data is. And the other points on the surface, it's just that the Bayesian inference is 1 point on the curve. It happens to be the one that is at slope 1. If you rotate the curve 45 degrees, you're looking at the one that's closest to the origin. But there's other points of the curve that make a different choice in the trade-off. Let's take it up a notch. Okay, we previously were looking at a situation where we had data and we were interested in inferring like a single global parameter, the mean or the cosmological constant. What if we're interested in something like compression? So we just change the diagram. Like it's just, we're in a different situation. There's pictures and I want to represent the pictures by like a message, some compressed message, some vector or something, right? That's what I want to do. Take an image, represent it as like a vector. What is the real world? What am I actually going to do? There's pictures. I'm not going to get to choose the pictures, but I get to choose like an encoder. I get to choose a thing, a machine that given an image spits out an output, spits out some compressed representation. That's the thing that I'm going to seek, the thing that I'm going to choose, the thing I'm going to form beliefs about. What the vector is that should represent an image. What do I wish happened? What does the ideal world look like? Well, if this thing really was a good description of the picture, I ought to be able to create the picture. I ought to be able to go the other way. I ought to be able to take my description of the picture, my compressed representation, and invent the picture again, right? I ought to be able to kind of go backwards. I might have some model or thing that I could use to explicitly rebuild the picture, some decoder or something. Let's just do the exact same thing. How should I set my beliefs about what the latents corresponding to an images are? let's do thermodynamics. Let's look for the one that's closest to what I thought was, going on anyway. And let's just, minimize the KL subject to constraint. Let's write it out. Let's separate the terms. We do that. We end up with this objective. We just reinvented the variational autoencoder, which you may have heard of. This is the elbow, the evidence lower bound, something you've seen people talk about, but this is what it is. It's a way of trying to set what you think your belief is about the latent of some variable, like how you should design the encoder in order to achieve the optimal trade-off between these two terms. One is a distortion, your ability to recreate the image that you saw, right? What is a good compressor? It's something that can eat an image, spit out something small, and then spit the image back out. That's what this term measures. What is it going up against? The cost, the KL, how expensive it is to write down the thing that you write down, how big your compressed representation of the image is. And these two things fight, they trade off. But in the space of all possible things that you could do, in the space of all possible beliefs you could have about what latents are in terms of images, in the space of all possible encoders that you could write down, there's going to be, you just, again, you give me an encoder, it's going to be a single point in this point. In the space of all possible encoders, we fill the space, but importantly, we do not fill the space. There's an edge. There's a set of ones that are maximally ignorant. There's a set of ones that are optimal.
So Alex?
Yes.
So I've received the sort of the instruction that I should so now and then sort of interject, and maybe if there is a question to then pose it in the middle of the talk.
Okay.
I just hate to interrupt the flow because it's such a wonderful talk. But so there is an observation by Adriano Barra, and it says, I have an observation regarding this very interesting discussion on the interpretation of KL cross entropy in terms of beliefs. This interpretation to me is not too far from the ancient principle sufficient reason by Leibniz. And in some sense, this was also pointed out by James. Is this something that you relate to?
Yes, I think so. So yeah, I mean, Laplace was sort of the first person to try to think about what they should set. There's this question of what you should set your prior beliefs to, right? What we've been talking about so far, I think, is a principle by which you could use to update your beliefs. But we didn't say what you should set your beliefs to be yesterday. At some point there's like the first day. What do you choose as your beliefs on the first day? And lots of philosophers have worried a great deal about how you kind of choose priors. And Laplace, I think the principle of insufficient reason was originally motivated by Laplace as a mechanism by which you should use to choose priors. And he was saying, if you know nothing, sort of start with the maximally ignorant distribution. And since Laplace was thinking in terms of sort of entropy rather than KL divergence, he would choose uniform distributions as his sort of prior. Before I flip the coin, I might as well assume that each side of the coin is equally likely. I might assume a uniform distribution and things like that. And I think that is a totally reasonable way to try to choose priors for lots of problems. I think things get a little more complicated in the continuous setting because uniform isn't reparameterization independent. It depends on the sort of coordinates that you use to describe some continuous space. So I think there's more issues. But as we're talking about here in the context of things like machine learning, the prior isn't necessarily, the prior is like a model. A prior is a thing that you could build that could try to describe the system. So, do your best, try your, do your worst, try to build the most accurate or the best model that you can and use that as your reference point. And I think, broadly, I think the answer to prior selection is how do you choose a prior? You do the best you can. It's just like in all of life, right?
Can you go back one slide?
Yeah.
So it's interesting that, so this looks a lot, of course, like variational autoencoder type of objective. It's just that the role of P and Q are reversed somehow, right? I'm just slightly confused. So, but it's not maybe not just notation. It's actually maybe deeper than that. I don't know. So Q for you is the set of beliefs for a person, right? Where in an autoencoder you would think that's the model of the world in some sense. That's P of X. That's the decoder.
Yeah.
So where in variation autoencoders you would have sort of an inference distribution Q, which I guess would be P of Z given X in your case, which would say QZ given X, which is your interpretation of the world of what Z could be given X, and you would sort of infer that distribution, but P is fixed in some sense. So can you comment on that discrepancy a little bit?
Yes. So yes, one, I use P's and Q's different than everybody else, and I apologize, and that's confusing, and I don't really have an excuse except this is the way I like to do it. But the broader point, and I think this is an interesting thing, is yes, the way that most people talk about variational autoencoders is very different. Most people believe that this dream world, the thing that they imagined was true, and they kind of push on it, right? They start with the generative model, and the generative model is the primary object. and that they do maximum likelihood on or something. And
Yeah.
I invite you to think different, to think that the primary thing of interest is actually the representation. That's the point. The reason you build a variational autoencoder is not to get a good generative model. That's not the point. The point is to learn the representation, in the sense that there are other strategies you could adopt to learn good generative models, right? Like you'd be lying if you said that the only point was to build a good generative model. You've made a choice. You've restricted yourself to a certain sort of form for your inference, and that should be the kind of primary character in the play, the encoder, the thing that you're designing. And we should think about things as a, from this representational perspective. How do I design the best encoding, right? And that allows us, I just think that's a more, one, it's an alternative way to think. And I think it's always useful to think about things multiple ways. Two, when you think about things from this sort of representational perspective, certain mysteries like posterior collapse are not very mysterious anymore, because they're kind of just statements about the geometry of the surface and things like that. So,
right. Okay. Yes.
So,
but for you, Z is that sort of things that live in our brain, or is this actual degrees of freedom in the physical world?
I guess I'm actually imagining the very sort of like, Z is the output of your encoder. You are going to build a machine, right? The machine is going to eat an image and it's going to spit something out, right? When you an image compression mechanism, an image compression algorithm, you run the code, image goes in, something comes out. The something that comes out is Z. And what we're trying to do is we're trying to design, right, what we think should be, what beliefs we should hold about what should come out. How do we design the machine? How do we design the encoder? What principle do we use to guide the design of that machine? In the space of all possible machines, you give me a machine and I could calculate these two quantities. For any machine, I could calculate its rate and its divergence, or its distortion. And it might live here, and it might live there, and it might live here, and it might live there. But in the space of all possible machines, there's an edge. There are some that are optimal. There are some that are better than all the rest. And those are the ones that are characterized by the solution to this equation. Those are the ones that are given to you by the beta VAE, by the elbow. They're not just any machine. Those are optimal in this sense. They are the ones that live on the edge. But all the ones on the edge are all equally optimal by this measure. And you kind of can't distinguish them except in their behavior. So there's this older paper of ours, Fixing a Broken Elbow, where we actually do this, right? We build a whole class of different architectures, and you can see that it looks like they trace out a surface. They trace out an edge. You solve this equation, you just change the beta, you do it a whole bunch of times. You can get all kinds of different solutions that all seem to live on some edge. They don't cross that line. And that line is characterized by solutions that behave very differently, right? What are we trading off between? Rate is how expensive it is to write down the thing you write down. Distortion is how good you do at recreating the thing. There are extremes, right? You could make a rate of 0 if I don't write anything down. If my machine takes an image and spits out the number 4, regardless of the image. That's maximally compressed, right? That is a fantastic compression algorithm that could turn my entire hard disk of images to, a single number, but I can't recreate the images, right? The distortion is very poor. On the other extreme, I could just save the images to disk. I could not compress them at all, right? The identity map as the encoder. That does a fantastic job. It achieves 0 distortion, but it's very expensive because I have to write down the whole image. And the things on this edge are making that trade-off, right? Here's some instances. Here's the images I send in, these black things. What I'm showing are a whole bunch of different reconstructions from several models, as well as, just whole cloth hallucinations. This model is sitting at something like 22 nats. It compresses the images by a factor of 4. When you compress the image by a factor of 4, it sort of basically keeps the entire image. As a human, these look the same. I mean, it's the salt and pepper noise is different, and it's sort of synthesizing the edges, but otherwise it's the same picture. I would say that this is like a fantastic, lossy compression in the way that I would use it. I get the same image out that I send in. And all I did was set beta equals 0 in this case, and got like an autoencoder or something close to 0. If I set beta equals 1, if I actually do a VAE in this case, because I had a powerful architecture, I get posterior collapse. And because of the shape of the model surface, the slope 1 point happens to be all the way at the left. And now this model, any image that goes in, it spits out 4, which is fantastically compressive, but it can't get the image back. Instead, when you ask it to decode, it just tries to invent a new image whole cloth, right? I don't know what you gave me. Here, take a new image. And you can see it just trying desperately to generate images as the reconstructions. But you move along this curve, you can there's the whole curve. You can explore the curve and you could find interesting solutions. Here's one that compresses this entire image into 11 bits. And you'll notice that when it does that, 2's go in, 2's come out, 0's go in, 0's come out. but not just the same two. Like there's semantic variation in the thing that comes out. Here, this 2 goes in, the 2s that come out, some of them have little loops at the bottom. Some of them don't. They're all 2s, but they're different 2s in a more semantic way, right? It's throwing away everything but 11 bits. And so you can't get the same image back, but you can get one that has the same character. Here, zeros go in, zeros come out, and they're all fat zeros. It sort of knows that they're zeros and it knows that they're fat, but it doesn't really know anything else. So there you go. 2 things you might have heard of. In so much as we're going to, pitch some of my stuff, we can continue this thread. Okay, so we talked about global inference for a parameter. We talked about building something like a autoencoder, some kind of compression algorithm. That's what we just talked about, something like a VAE. What happens if we have other data? What if there's other things that we know about, other things that we care about? What if our images have labels? Let's just do it again. Let's just talk about both what are the constraints that we satisfy, the sort of causal constraints, what's our engineering setup, and what do we wish were true? In the real world, if I have images and labels, that distribution of images labels, I don't get to fix. The world chooses that. What I get to design is my encoder. And for practical reasons, I might require still that I can encode images without knowing the labels, because eventually I'll want to try to predict labels without knowing them. So I say that this is what I'm interested in, and I want to, again, look for this belief, a principle that can help me guide these beliefs. What do I wish were true? Well, if I did a really good job of compressing images, I might be able to predict the images as before. I might also be able to predict what the label was, right? That seems reasonable. So this is sort of my prior. This is what I wish were true. Take the KL divergence, separate out the terms, and you get 3 things. You get the same 2 we had before, distortion and rate. Now there's a new guy at the party. How well you can predict the labels that you didn't see. But just as before, now instead of a 2-dimensional space, is a 3-dimensional space for any encoder you choose, for any beliefs that you have about what the latents are for an image. You could calculate these 3 numbers. You could do a single point in the space. You could fill the space, and there's going to be an edge. And Pratik is going to, I suspect, not to talk for him, but here's a paper, a fantastic paper of his, where they actually dig much deeper. Once you identify that this thing is thermodynamics, and you can actually, identify derivatives and stuff, you can design things like ISO classification paths on the surface. Just like in thermodynamics, we can talk about things like isochoric paths or adiabatic paths. You can actually move on the surface between optimal things in particular ways. And Pratik did fantastic work in that direction, which I hope he'll talk to you about, because I'm like lobbing him setup. For my own purposes, even though I didn't think about it back in the day like this, one of my kind of first papers in this room was studying this objective, this thing, but with gamma equals 0, which we called the variational information bottleneck. It's just one edge, a 1-dimensional edge of this 2-dimensional surface. Where you're trading off between the cost, again, the complexity of your representation of things, and how well you do at predicting things. And there's a trade-off, just as before. Just to kind of, I don't know, hopefully we'll get to the code, but just to kind of give you a taste, right? Ordinarily, when you train a classifier, it takes an image and it spits out a vector, right? The thing comes out of the machine, the thing comes out of the encoder, and it's just a vector. It's a point in a space. If you ask something to give you a 2-dimensional point and do classification, you get something like this. MNIST digits go in, a single point in the space comes out. But that's, again, it's expensive to specify an exact point in 2-dimensional space. It takes a lot of bits. If you train this variational autoencoder, we're no longer certain about where the thing is in space. We give you back a distribution. The encoder takes an image and it tells you its belief about where the thing lives in space. Instead of being a single point, it gives you a distribution. It gives you, here I'm visualizing it with like the 1 sigma ellipses. And you'll notice that they all overlap. The encoder doesn't see the differences between the individual images anymore. It only sort of sees what class they are. And that's kind of the point. And that's how this can be useful. Because if you train an encoder that tries to do classification, but it throws away information that isn't relevant for classification, those classifiers can do better when you try to break them, right? Traditional classifiers are very sensitive to things like adversarial examples. You take an image of a bird and you just add a little bit of impulse noise, it doesn't think it's a bird anymore. But these kinds of classifiers, if you look at other points on the surface, if you move along the curve a little bit, you can find ones that are more robust to these kinds of perturbations. And that's like for a large scale image data set like ImageNet, we kind of can show that we achieve robustness to common corruptions and, paper pitch. The last thing I want to leave you with, and this really is the last thing, is really just kind of this other workshop paper is we just go one more step. Take all the diagrams we talked about and kind of stick them all together. And I think that legitimately describes the sort of causal setup, the real world that we're ordinarily in most of the time, where we have images, we have labels, we're interested in building machines that spit things out, but we're also setting the knobs in the machine. And if the knobs in the machine are also something that we want to have beliefs about, we can add them to this diagram. The only, this is just one diagram like any of the others, but what I think is kind of interesting about this particular diagram is when you write down the natural target and you do the same thing, KL, you split it into terms. There's 4 terms because there's 4 variables, but that single objective now really encapsulates all the things that we talked about and more. This one 3-dimensional surface in a 4-dimensional space actually contains most of the things you probably heard about, because you can kind of move around on the surface, choose the coefficients, go to different places in the thing. But in particular, if you set all the coefficients to 0, you rotate the thing to an extreme and you just go for classification performance, you build an ordinary classifier. You throw in the rate, you explore that 1-dimensional boundary on the surface, you get the variational information bottleneck. You just go for distortion, you build an autoencoder. You do distortion plus rate with coefficient 1, so you rotate it 45 degrees along that axis and you minimize it, you get a VAE. You allow yourself to explore 1-dimensional edge of the surface, you get a beta VAE. You do all 3, you get something like Pratik will talk about, or a semi-supervised VAE. You go to the other side. If you want to be explicit about the beliefs that you form about the parameters of your encoder, and you do it with coefficient 1 for some reason, you build a Bayesian neural network. That's exactly the objective satisfied by a Bayesian neural network. You explore a 1-dimensional surface there, you get this information bottleneck Lagrangian from Achille and Swato. And I guess really, the point is, if all of these things are just edges of a single surface, maybe it's useful to think about the surface. Maybe it's useful to kind of adopt this bigger picture where all of these things are more the same than they are different. And that, I think, is basically what I had to say. I realize it went a little long, and I do have some code. I don't know where we're at. I think, but I have some code I can show, or we can talk about questions.
Yeah, so I thank you very much, Alex. So let me see if I can, is there any way that we can clap? I'm not sure, but anyway, I'll clap for you.
Thank you.
It was a fantastic talk, actually. It was very lucid and good to understand. So if people would like to ask questions now, I think it's good maybe to ask a few questions now and then move to the code. And then after that, we can do another round of questions, I think.
So how poor was I? How much time do we actually have between?
Well, we're only 10 minutes behind, so it's okay.
Okay.
So I think we have until 6:30, right? Total
time.
Oh.
Yeah. We usually it's like 40 minutes of the talk and then 20 minutes of the code walkthrough. And usually we start like 5 minutes after. So you're only 10 minutes, and we will blame it on Adriano's philosophical question.
No, but I think it was a great question. Thank you.
Yeah.
Can I ask a quick one, Max?
Yeah, of course.
So Alex, this is fantastic, and having even covered it myself, I was many of my students were slacking in the back and saying, this looks very familiar but different at the same time. So in Thermo, we have preferred ensembles for different kinds of problems, right? So when we want to solve a particular kind of problem, we know, okay, we want to do an isochoric process or isobaric process, then we would go to corresponding NBT ensemble or NPT ensemble and things like that. That then sets the sort of right loss function in a sense, right? Because it sets the ensemble, it sets the loss function, and so on. In machine learning now, how do we, given a problem, right? How do we sort of bring back this notion of which ensemble to pick? Now that we've built this stat thermo analogy, given a problem, is there a way in which you think about which ensemble to choose, or equivalently which loss function, of course, but is that something you've given thought through?
Yeah. So I think I guess in my own head, the way this works, right, is kind of, here we did it 3 times, right? And the thing that decides sort of which. Okay, let me try this. At the end, I showed you that, like thermal or whatever, like this particular objective with 4 terms, encapsulates all the others, right? That we talked about, right? Like Bayesian inference, variational information bottleneck, VAEs are all like parts of this one thing. that's exactly the same sort of thing, right? The difference between something like a microcanonical or a canonical ensemble is just a question of which variables you are tracking, right? Which things you're tracking. Are you tracking the average energy and the temperature, or like, are you describing things in terms of fixed temperature or not? So just like in kind of thermodynamics, like the thing that decides, engineers talk about physicists talk about free energy because we tend to work with systems that are at fixed temperature but in closed containers. Chemists talk about Gibbs free energy because they tend to, and the corresponding ensemble, which I forget the name of, because they tend to do things in beakers that are exposed to air at constant pressure. So there really are just sort of design considerations that govern which ensemble you want to work with. In the same way that we were doing here, right? I earlier on, if all you're interested in is the cosmological constant and you're going to observe pictures, then yeah, start with just those two kind of variables of interest and work in that ensemble, the one that sort of only looks at the Kale divergence with respect to the parameter distribution and the prior and the likelihood. That is a different ensemble than the one that you're looking at when you do a VAE, but it's because you care about different things. In the VAE setting, you care about reconstruction, you care about distortion and rate. Those are the kind of two things that you're tracking. So I don't know if that answers.
It did, thanks, yeah.
Can I ask a question? So there's one thing that you didn't consider, which should be able to fix some of these constants at least, which is generalization, right? So how well am I going to do a future data for a Bayes model? It would basically set the temperature to 1. So how does that? Can you find other reasons to set some of these constants?
Yes. So I love the question, and I wish I knew better. I mean, that's honestly what kind of keeps me up at night today, right? Is that exploring that. So one paper, another kind of workshop I worked on, it's sort of trying to be explicit, right? Like, let's bring to the party, let's consider a different ensemble where future data is like the party and also sort of show the program. Use that if we can see, we can use that to try to guide, questions in like this paper, variational predictive information bottleneck. I'm kind of looking at the Bayesian setting, explicit about the tomorrow of their data. And I try to describe things, and I look at whether the same kind of thing can guide me in trying to better choose, shoot for better generalization performance there. And like much of my work today that I'm working on is focusing on that generalization aspect. So I think it's a fantastic question. I wish I had the answer for you. Check back in a decade and we'll talk, right? Like
sometimes a good question is the half of the answer. So I think a good direction to move into is already super interesting. So I have one other question, if I may, because I'm just so fascinated by all of this. So I remember I read a paper by Janes a while ago, where he basically argued that for diffusion processes, it's best not to describe it trying, with microscopic physical laws, but really to try to describe diffusion as an inference process. That's far easier, and you will actually get the right answer. So basically in AI, what you describe is basically an epistemological theory of our inferences about the world, right? There's a world, and this is our beliefs in our head about the world and how they evolve. Now, this is probably also true for thermodynamics to some degree, but in general, do we think that when you describe laws, physical laws, should we interpret them like this as basically our best possible description about information processing and how we sort of can make inferences about the world? Or are we actually describing the ontological world? So do you see what I'm trying to get at?
You're asking an extremely deep philosophical question, which I have no authority to provide an answer to, but I can give my opinion of, right? Yes. And I think my opinion is that it's the former rather than the latter, in the sense that I was thinking the other day, honestly, I mean, there's this deep question about ontology, but if I've got a box of gas in front of me, I'm content saying that box of gas has a temperature.
Yes.
Or it has a pressure, or it has an entropy. Like, that's a thing that I'm kind of willing to give ontological weight to, is that it has a pressure. But honest with myself, that, especially the entropy, but also if I describe the classic system, it doesn't have a well-defined single pressure, right? That isn't a property of the state. that is a property of the derivative of the equilibrium distribution over states that live on the surface that corresponds to some particular average energy or something. So I guess, like, I don't know, I'm very pragmatic with these kind of philosophical things, but I recognize in myself that when I look at a box of gas, I'm willing to say that it has a pressure. And I'm admitting that saying that it has a pressure is sort of saying that I believe that it's okay for us to talk truthfully about these models of systems, even if we don't think that those models are, what's the philosophical word, but reductionist or whatever, right? Like statistical mechanics is a different way of describing the system than classical mechanics, and it gives you different things you can talk about, like pressure. And I'm willing to say that those are real, even though those are not the purely reductionist way of describing the system. Those are emergent.
You could go one step further and ask the question about gravity. So I'd like to say two bodies that would, so now the question is, of course, this is all just descriptions, macroscopic descriptions of things that we can measure conveniently in our measurement machines, right?
Yeah.
And some people actually describe gravity as an entropic force. So they basically say gravity happens due to the fact that there is degrees of freedom that the system responds to. So you could even, apply similar arguments there and basically say that, everything, every physical law that we write down is the result of, some kind of epistemological description of how we believe the world really works, but it's not really the work at all, not the world at all, right?
Amen, Max. I'm with you. Yeah.
All right. Okay. Good.
Yeah.
All right. So we should move to something more concrete, code. So
Sure.
Why don't you go to code?
Yeah. So I think. Oh man. Okay. So is this? Do you see code now? Is that showing up?
Yes.
No?
Yes, we see code.
Oh, excellent.
Yeah, if you can zoom in just a little bit, Alex, I think that would help. Perfect. Yeah.
All right. So here's code. So first, let me say, So if you go to, you might be able to see it up here, github.com/alexalemi/VIB demo. You'll be able to find this demo thing. I think it's an old repository, so you should be able to search for it, just Alemi VIB demo. I added a notebook like last night, which is supposed to be a sort of simple demonstration of VIB, like one of the things we talked about, right? Like, what does it actually mean or look like to train these kind of encoders that give you distributions? And so this is supposed to be a demonstration. It runs in Colab. If you go to the GitHub thing, you can find the rendered thing, but then I designed it to run in Google Colab. So if you click this little button here, open in Colab, you can run it yourself. So I'll try, this isn't like polished. I'll try to maybe update it, today or tomorrow, make it like a little better and cooler and stuff. So it'll live on beyond this talk, that people can check it out. But I guess I just wanted to show, here I'm doing things in JAX. If you don't know about JAX, you should really, really check it out. It's a fantastic framework for doing these kinds of things based on like function transformations in Python and stuff. It's really fantastic. I'm downloading MNIST because why not? And I have a bunch of utilities here, but I'll kind of show you what this thing kind of looks like. So, okay, let's build a model. Let's build a classifier. So here's in JAX, in Flax in particular, which is a library that you use with JAX to build neural networks. This is what it looks like to kind of build a encoder. The encoder is going to be the machine. The machine is going to take an image as the input, and it's going to spit out a vector. And how are we going to design that thing? What I'm going to do is I'm actually going to just do like a fully connected feed-forward neural network. I'm going to take the images. I'm going to kind of flatten them. I'm going to send it through a dense 512 hidden unit layer. I'm going to use a JLU nonlinearity and layer norm for no good reason. These are just, the kinds of things. This is the alchemy. There is alchemy in deep learning, and the alchemy is, how do you design the architectures? How do you choose the initializers? What optimizers you use in order to power your efficient search in the space of all possible functions? What I want you to do is really just think about it as like, you're trying to search in the space of all possible functions. You kind of like, embark in the alchemy in order to efficiently power that search. But what you should seek are objectives that you can write down that, are of the form. There's like these variational ones in the space of all possible functions. What's the one that's best? And that's what the objectives that we were talking about are, right? They are ways for us to evaluate for any belief that you have for any encoder, for any machine, you could evaluate it. And then we're just going to look for an objective that allows us to search in the space of all possible encoders. So we start with just ordinary classification. We build an encoder of a particular size. In this case, so we can visualize things, it'll be two-dimensional. And then we build a classifier. So this is the thing that once observing that two-dimensional code, that like compressed representation of the image, it tries to predict the label. And this will just be another little one hidden layer neural network. I'm going to build another object that holds all these things together. It just kind of holds all the parameters together. It will have the encoder and the decoder. And when I call this thing, when I hand it an image, it will encode it and then classify it and return. And now we're just going to train this thing. So we're going to train it. There's some kind of setup. I initialize the thing, and then here's my loss. So for the ordinary classifier, what I'm going to do is in JAX has a really nice automatic differentiation tool kit. It's based as a function transformation. So you want to write a function whose argument is the thing that you want to take the derivative of. And then it just like automatically, right, calculates the derivative of any function, right? The machine learning is practical these days because automatic differentiation exists and you don't have to write Jacobians anymore like I did in grad school. So our loss function is going to take the parameters, right? The checkpoint, the millions of knobs that I want to tune. In this case, I think it's 128,000 knobs, and it's just going to score it. In this case, we're just going to go with a classic objective. So we're going to take that parameters. There's a little bit of setup. I'm just going to throw all the images through the model. I'm going to get out the representation. I'm going to interpret that representation as if it's logits for a categorical distribution, right? I'm trying to assign a probability for every one of the labels. I'm going to evaluate the probability that the label that actually came with that image would be assigned given by this machine. I'm going to take the average over the batch, and that is the thing that I'm going to return. That's the thing that I'm going to try to optimize, this sort of classification error, the C term that showed up in the slide, in the talks. And that's the only thing that we're sort of set all the other coefficients to 0, just like optimize this thing where the classification error is minimized. The way that you do training in JAX with Optax is kind of you write a loop that kind of looks like this. We just take the gradient of our loss, we kind of get those gradients out, and then we have a little name tuple essentially that stores all kinds of statistics during our optimization trajectory. We use the library to update what the update should be, how we should adjust the parameters, and then we apply those. In this case, I'm using something like, I think I'm using AdaBelief. It's just one of these alchemical optimizers that does a good job. And then we just update our state. So if we do that for this classifier, here I'm kind of spitting out some statistics. We notice that, we train for a few thousand steps. What we're getting is on the training set, we're getting basically perfect accuracy. Whereas on the test set, it's something like 94%. Is this actually still running? Nope. Okay. So I should have done this when I started talking. It's going to take just a couple minutes, but I think the images are still there. Oh, now I just got rid of them. Oh, well, that's disappointing. So Colab times out if you don't update it. I opened this at the beginning of the talk and then it times out and it disconnects you from the session. You have to reconnect. So now I have to, redo everything. So if somebody had another question, this would be a great time for another question as we wait just the kind of hopefully 2 minutes to get this thing going.
I figured out that there are questions in the Q&A that I missed, and so we can just go over the Q&A questions actually. So Rachel Kirchin is asking, so this is going a little while back into your talk, I think. So what's the analogy for the beta parameter / temperature in the VAE example?
What's the analogy for the beta temperature or the temperature in the VAE example? So it is a temperature. Let's back up. What's temperature? So in thermodynamics, temperature is just the derivative of the energy with respect to the entropy. There's this optimal surface, and at any point on that surface, there's a derivative on the curve, and the temperature is just the derivative, right? It's du ds, or I guess technically it's 1 over du ds, whatever. All it is that derivative. So what is the beta in my beta VAE? It's the exact same thing. It's on that surface, there's a derivative, and the derivative is, d distortion, d rate, the two things that we are tracking. And beta is just the measure for the trade-off there. If it's 1, what it's saying is while you're satisfying the objective, you set beta to 1, you're saying, it's the conversion factor between those two things. When you're building a machine, you are going to put just as much weight on it being able to reproduce, 1 for 1, with the cost measured in KL. If you set the beta to 0.1 on rate, you're saying you care more about distortion. You want to recreate images better than you care about their cost. And that's what kind of moves you along this trajectory. The beta really is just the derivative of the surface. If you set it to some fixed beta and you optimize, it's like we said earlier, it's like taking that whole curve, rotating it by some amount and just looking for the minimum. All right, this thing's back up and running. It's training again. So here you can see sort of how fast this thing goes live. Most of the time was not it doing anything. It was it reinstalling packages that I need at the top. So Colab is actually, if you haven't played with it, it's pretty cool. You can kind of do things like this. This is running on a GPU in the cloud and stuff. So here I wanted to show, okay, the final train accuracy is near perfect. We can actually visualize what this thing is doing. So now that we've built this machine, the machine takes images and spits out a two-dimensional representation, and I can visualize that because it's in 2 dimensions. So for every one of the images, I can draw a point, and I can color them according to what the true label is. And so you can see a 2-dimensional classifier. What it's doing is it's kind of taking all the images and it's kind of splaying them out into this thing. There's some in the center, and then the different classes seem to sort of separate. In fact, we can do a little bit better. We can draw some of the pictures of the digits on here, sort of where they are associated, and you can start to see the differences between the different classes here. It put all the 3s kind of down here, the 8s over here, the 5s over there, the 7s, the 2s, the 4s, etc. All right, let's make this thing a VIB network. So what's different? Instead of looking for a machine that assigns a particular point in the 2-dimensional space, we want to assign a belief about what point it should be at. We want to return a distribution. So what we're going to do is we're going to use the same encoder architecture to generate numbers. But then what we do with that is we build a distribution. In this case, we're going to build a Gaussian, a 2-dimensional Gaussian distribution. So the 2-dimensional Gaussian distribution is going to have a mean, a location, and then it also has a covariance. And for 2 dimensions, the covariance has 3 numbers, like real numbers that you need to specify, right? You should think of it as like sigma x, sigma y, and sigma xy in order to specify the kind of relationship. But we're otherwise going to sort of do the same, right? We're going to change the objective. We're going to change the rule that we use to score this thing, but we're going to search in the space of all possible machines that could encode. It's just that now our encoder, instead of spitting out a point, spits out a distribution. That's kind of what I'm doing here. The decoder is sort of the same. Once we spit out a distribution, we can sample from that in order to get 2-dimensional points. And then we can pass those samples to the classifier, just like we did before, use the same classifier. And then the objective is going to be here. So like we said before, now we actually have sort of 2 terms. We've got the classification error, which is exactly the same as we had before, where one of the things in our objective is how good we can do at predicting things. Take the image, encode it to a distribution, sample from the distribution, feed that to the classifier, and ask how good you do at predicting the right label. The other part of the objective is how expensive it is for us to specify our belief about where each image should lie in the 2-dimensional space, the rate. And the rate is here. It's the KL divergence between the distribution that we assign to an individual image, sort of after the fact. You look at the image and you decide where to put it in space with respect to some marginal, which in this case, I just chose to be a fixed 0-1 Gaussian. So, I had to choose a measure on the space. I'm going to choose that measure, as you move away from the origin, things are less likely or should be. And this rate is really how expensive, how much it cost for me to express what that one image was. And my loss is really just, here, I'll show you. The loss is just C, this classification error, plus beta times the rate. So if beta equals 0, this is more or less the same objective that we had before. The architecture is slightly different because there's a distribution instead of the thing, but it will learn to set the covariance to 0. Here with this beta, this is actually VIB. We could train it. It's the same training loop. And you can train this thing. And here I'll start training it some more just to get some more. What does this do? So now, instead of each image being a single point, each image is a distribution. And I can show you what that looks like. So here are input images that go through this trained thing. And here I'm showing the entire 2-dimensional space. Instead of a single point, it's an entire distribution. And here I'm visualizing the probability density for every one of those images. And now you'll notice that here's a 1 and here's a 1. That one gets encoded as that distribution. This one gets encoded in that distribution. Those 2 distributions are very similar. They're nearly the same. They're nearly the same in a quantifiable sense. We can measure this rate, this KL, and interpret it in bits, the amount of information required to sort of specify these things as being distinct from the marginal. In particular, I can show you the way this thing works is here's those 2 ones, the 2 different ones. You send it through the encoder and you take samples. All of the orange dots are different 2-dimensional samples you would get from the encoder that we trained. All the blue dots are different samples you would get from the encoder that we trained for the other one. I'm drawing a 1 sigma contour as an ellipse for both distributions, and you notice that they largely overlap. Imagine for a second that you are actually using this machine, right? This machine is stochastic, it's not deterministic. You get an image, you send it through the thing, and you take a single sample. If I only gave you a single orange dot, can you tell the difference between a single orange dot and a single blue dot? Not really, right? There's a real sense in which those are, the encoder has forgotten. You would no longer be able to tell the difference between those two images. That's been thrown away. The thing has actually thrown away some of the sort of information in the image. And so we can actually look here. I just look at the means of all the encodings, and it kind of also looks thing. But if we actually visualize now for all those images, we draw an ellipse to visualize the distributions. You can see that this one, because I put beta to some appreciable value, has learned to really throw away almost all the information. I think we could check the rate for this thing is something like 2.3 nats. So that's, what is that in bits? 2.3 nats is, in either case, less than, I think, 10 bits, probably about 8 bits of information that it keeps. It takes the image and it throws almost everything away, and all it keeps is more or less which class it was. You'll notice like these ones in particular, almost all the ellipses are right on top of each other. You can kind of see right through all the ones, and they don't overlap. Some of the other classes do show some variation. Sometimes, if as the image differs, it will morph, you know, how it expresses it and push it slightly into slightly different regimes, or, you know, it might make it overlap in a particular direction because it's sort of unsure of what things are. And I mean, I think that's more or less it. I can show you like, you know, because this thing is stochastic, there's also, it also allows it to express uncertainty in a sort of distinct way. So here's that's not the one I wanted. Yeah. So here's one image that I tried to look for images that it was doing a kind of poor job of predicting the correct class on. And so here's one image, and here you can actually see that what this thing does is if I sample it multiple times, I take the stochastic encoder, I send the image in, I get a two-dimensional point, and I classify. I send it in, I get a two-dimensional point, and I classify. I send it in, I get a two-dimensional, I classify, and I sort of average those predictions. I can now get a much more, I can quantify uncertainty in a better way. And when you try to measure these models for things like expected calibration error and things like that, they tend to be improved. Here you can see that this model, it actually does assign 5 as the most common class, but it, you know, it says that there's like 15% chance that thing's a 3, 15% chance that thing might be an 8. And as a neural network apologetic, I can kind of see where it's coming from, right? That might be a 3-looking thing. Here's actually some of the ones it gets wrong, and we could maybe sort of decode this. So yeah, it looks like, so this model is, this image right here is actually supposed to be an 8. Can you see my mouse or no? Yes? Okay. This is supposed to be an 8 in the data set, but the network, the most likely class it assigns to it is a 7. And, you know, I can see where it's coming from. These are actually most of the digits that it has trouble with, and I can kind of understand why. So I guess like the thing I wanted to emphasize, and you can kind of play with this yourself, was the kind of stark difference in, like, operationally, this thing is doing something different. Instead of taking an image and spitting out a single point in two-dimensional space, you take an image and it gives you a distribution in that space. It assigns a belief to where the thing should be located. But by doing so, you can actually ignore most of the features in the image and learn something that might be, you can imagine how it might be more robust to things like adversarial perturbations or out of distribution samples, or it might be able to express uncertainty in different ways. And I think I'll probably, in that same repo, there's some other demo code. And like I said, I'll try to add some more and use this as an excuse to kind of clean this thing up for future viewers who will kind of go for it. I think I'll come back over here and
there was actually a question on the code.
Oh, okay, sure.
So somebody was asking, Rachel was asking, how much more computationally costly is the VIB approach compared to the conventional one? Are you drawing n samples by brute force such that it costs nx as much, or can it compute directly on the distribution somehow? So
I am sampling, and so there's an additional cost, but that cost is honestly not that bad, because so the way that I tend to use VIB in practice is for something like a traditional image classification data set, the encoder is going to be basically the same. You're going to use some big ResNet, you're going to use some big inception network or something, and that's going to provide the parameters for the distribution. That thing only still needs to run once, right? You take the image and you encode it in order to find the parameters, like which distribution you want. That only needs to run once, and that's the expensive bit. Once you actually find the distribution, that's happening in usually a lower dimensional space. I honestly, a lot of times just use like 5 or 8 or 10 dimensions. And those samples usually go through a classifier that's only a single layer or something. And yes, it's not required to at training time to draw multiple samples, but if you draw multiple samples at training time and average across them, you tend to get lower variance in the gradients, and it kind of trains better in the result. There, you do have to run those samples through the classifier multiple times at the cost of n evaluations, but that's the cheap part, right? That's like one hidden layer working in 32 dimensions rather than the ResNet 101 that's eating the entire image. So there's really not an appreciable kind of extra computational cost at the top. Training is a little slower. It's slower to converge because it is stochastic, right? This thing at training time, especially if you're in the highly compressed regime where these things have a lot of variability in the things. What I've noticed is, training train for longer epochs and stuff in order to get things to kind of settle in. But once the thing is trained at inference time, there is an additional cost if you want better predictions given the n samples at the top. But that's it's a negligible cost compared to the encoder stack in real problems. So you don't actually, yeah. I mean, that's honestly, so in some of the other papers, things like IB is half Bayes, like this is, I think the reason why I like these objectives is I think there's ways to get some of the benefits you get from a fully Bayesian approach without having to be fully Bayesian. We don't have to, in a Bayesian neural network where you try to be Bayesian about all the millions of parameters of the neural network, you have to rerun the whole network multiple times. Here, we are still doing stochastic inference. We still have a distribution, but it's happening in a lower dimensional space just at the top, just in the kind of final layers. And that's part of what I think is attracting to these objectives. Can we capture the benefits of Bayesian uncertainty and calibration and stuff without the full cost of really trying to assign a distribution over what I believe all the million knobs in the neural network are? And
in the end, of course, all the uncertainty and have to go through the last layer before you make a prediction. So there should be some distribution from which you can sample at the last layer, which would capture all the sort of fluctuations below. And most likely it is Gaussian because of the central limit theorem. So it seems very, very reasonable. Right. So I have another question, which is fascinating. What is the analogy of a phase transition in machine learning in your framework?
Yes, perfect. So it's there. Oh man, I think I had I thought I had a slide at some point. Oh, I must have got rendered from the extras. But there's a fantastic paper by a colleague. Oh man, I'm gonna butcher the. A colleague at DMind. Okay, what's a phase transition in thermodynamics? So a phase transition in thermodynamics is there's this optimal surface, right? And the optimal surface has to be convex. But sometimes for certain systems, there are regions of the surface that are sort of flat, where you can go from 2 points with the same derivative, right? There's a flat line, there's a facet to the surface. And what that means is for something like, water, as it boils or something, at certain pressures, the region is flat in a certain region where you can go, as I change the temperature, remember the temperature is a derivative, as I change it from, tau naught plus epsilon to tau naught minus epsilon, I move a big distance on the surface because the surface is actually flat at that place. That's what a phase transition is. That's all it is. It's identifying a certain geometric peculiarity of the surface where things are flat. These same flat facets can occur in machine learning systems. And actually, Danilo Rezende has a fantastic paper called Taming VAEs, where they actually demonstrate this for a VAE-like system, where they built a data set that was like hierarchically structured. They had, imagine you have circles, but then the circles are made up of circles, which are made up of circles. And they trained a VAE on this, and they actually traced out the rate distortion curve. They tried to trace out this frontier and found that there were places on the frontier where they had, diverging second derivatives, where they had kinks in the surface. Instead of flat bits, they had kinks where the derivative would, undergo a thing. And those corresponded to when the VAE was learning different degrees of the hierarchy, right? Sometimes it could only reconstruct the big circles, and then it could learn to reconstruct the circles within the circles, and then it could learn to reconstruct the circles within the circles within the circles. Those corresponded to kinks on the surface where you had diverging second derivatives, which are exactly what phase transitions are for physical systems.
Yeah, I think they're also described in information bottleneck papers. Yeah. They also describe these. Okay, how much time do we still have? We are at 27. I could still do one more question. until we get at 30. I'm just looking at the chairs a little bit. I'm not sure how bad it is to go over time, and maybe actually Alex has another commitment. I don't know.
Well, I'm content to hang out if people want to hang out, but
Yeah,
leave
we
it to
can probably
them.
do a few more minutes. We also want to make
Okay.
sure that we capture your thoughts, Max. Usually we ask the session chair also to share some insights.
Ah, that's right.
So we probably should maybe get to that first, and then maybe if there's any one last question, probably. But I think we want to ensure that we capture your insights.
Well, yeah, so I almost forgot about that actually. So now I need to produce my thoughts, which is interesting exercise actually. So first of all, I want to thank Alex for a wonderful talk because it was extremely educational. I mean, it's the way it was presented was absolutely brilliant, and I learned a lot from this. Yeah, I just have a lot of questions about how this maps onto physics. I'm sort of fascinated by physics. So to me, the analogy with thermodynamics is very apt. It certainly feels like it's the right way to describe the various degrees of freedom. But as I said, I also feel that some of these, you're on a surface, so you're adding sort of a degree of freedom, but some of these degrees of freedom should be resolvable when thinking about generalization performance. And I feel that I guess you could search over them now in this new framework by hyperparameter optimization, which might make it much more robust. And so I guess I also already explained my thoughts about the fascinating problem of what are we actually describing. So clearly in AI, we are always describing our knowledge about the world, and we are updating our knowledge about the world, and it's very clearly epistemological. Where in physics, I'm not so sure that that's always the case, although I'm inclined to think that, that's exactly what we do as well, even when we describe sort of fundamental laws of physics. I'm also very interested to think about the relationship to chaos theory. So when you think about a theory like this, then we sort of summarize all the underlying degrees of freedom by a probability distribution. But there is a very deep theory that describes the precise relationship between sort of these underlying degrees of these deterministic underlying degrees of freedom and how they end up being well described by a probability distribution. So many things, many details cannot actually be captured, and other things can actually be captured. And the things that can be captured by sort of more macroscopic degrees of freedom are the ones that are well described by these sort of quantities that you described. And it's kind of very interesting. And that also relates to yet another concept, which is a renormalization group in physics, where you start with a system with lots and lots of degrees of freedom, and you sort of choose to average away things and until you get to degrees of freedom that you can describe by your macroscopic and you can measure in your physical systems. And it feels that the things that you described here are in some sense the things that we like to think about in machine learning. So these degrees of freedom, that you sort of these thermodynamic quantities clearly are the things that we like to think about, the macroscopic things that we like to think about in machine learning. And just I wonder, are there more things? What other things are there, and can we learn them, right? And maybe that's what in some sense deep learning is all about. In some sense, in deep learning, we're also trying to learn from data the macroscopic quantities that we like to think about, which are the things, the abstract quantities which are appearing at the top of our neural network somehow, that are where we start to sort of average out sort of degrees of freedom, much like in your sort of VIP network, right, where you have an information bottleneck where you talk about removing details about the actual input. And that's the same process as abstracting away things, details that you're not interested in, and capturing them at a higher, at a more macroscopic degree of freedom. And you sort of, in some sense, your model explicitly encourages this process in a sort of very principled way. And so I'm very intrigued whether there is a relationship between abstraction and renormalization group versus your framework where you can sort of now describe this in a thermodynamic way, which is very suitable, because in thermodynamics this is also precisely what people do, right? In order to find the degrees of freedom, which are the correct macroscopic degrees of freedom to describe systems and to describe phase transitions and all these kinds of things. I think there's an incredibly deep connection between this and Bayesian learning. So I think that's and information theory as well. So the fact that in Bayes or in minimum description length, I guess that's a term that you didn't quite mention today, but the minimum description length is also one of these theories where you basically try to it's sort of a combination of Bayes and information theory, where you try to say how many degrees of freedom would I need to describe this particular system, but also at the same time still being able to sort of represent the system. So you want to maximally compress, and one way to do it is to just imagine, how do I send information from me to you, right? And there's a sort of and so maybe this is another interesting dimension, which is the finite dimensional side. If you have an infinite dimensional system, this question looks very different than if you have a finite dimensional system, because now you have to say something like, well, I cannot build an incredibly large, complicated model where I use all these parameters. I have to encode all these parameters, which will cost me something, because I will have to send these parameters to you as well, right? And then given the parameters, which is now acting as some kind of prior under which you can then encode, I can then encode the actual data, which is the latent variables, first for every data point, which can now be compressed, and on your end, because you have the parameters, you can now decode it, and then maybe also sort of errors that you can still so there in that setup, you do have, I think, an answer to what is the right trade-off, because that it basically tells you what's the best way I can send this information to you for a finite amount of data, and that basically tells me, precisely what is the trade-off between all the terms. Yeah, and so there's so many deep, things that chaos theory clearly actually also talks about this, and also sort of computability even, right? Can you compress something at all? I mean, it's an uncomputable whether you can compress further, and how does that tie into these? So I feel there's so many super deep questions around this, and I'm very happy that you took the effort to go through this. I learned a lot from all of this, and and it feels like a very beautiful unified theory that I will certainly explore in the future as well. So thank you very much.
Oh, yeah, thank you so much. Like honestly, I think I'm raising more questions than I'm providing answers. But I guess what I find exciting is that I think this, it creates a lot of really interesting questions. And I guess the other thing I'd be remiss not to mention is, I think your other question, connections. I think there's connections to all kinds of things, minimum description length and stuff, information theory broadly, but also with regards to things like renormalization group and which measurables, are useful or not useful in even things like diffusion. I'd be remiss if I didn't mention, my old advisor, Jim Sethna, and their group has been trying to answer like that specific question for physical systems and made a lot of tremendous progress. And I guess like it feels like, all of these different kind of fields are all trying to get at it. It feels like there's some deep question at the core of all these things, and I'm not sure I even know how to ask the question yet. But I'm excited to brush up against it. So
I totally agree.
I don't know if James might want to say something. He is in the audience, so I'm not.
Hey, Jim.
I think this is a fantastic development that we're seeing emerging, not of what we expected, which was some kind of statistical mechanical description, but thermodynamics turning into a way of organizing what has always been mysterious to me. It's a vast number of different machine learning problems. It's just wonderful. And I am deeply interested in the connection between this and generalization. The two exciting new developments are yours, this thermodynamic description, and some work in machine learning that seems to indicate that you can train a neural network to get perfect answers on a data set, and by by making more and more parameters, you get better descriptions. And I really like to understand both of those at the same time and in the same portion of my brain. It would be great.
Yeah, cool. So yeah, so I think we are over time. Certainly, I'm being called down for dinner. So
Sure.
I know I think there is a few questions. Maybe if people want to stay on, I don't know, to discuss these things, totally go ahead. I want to thank Alex one more time, and also the organizers of this wonderful workshop. From now on, I'll try to make time to go to these talks, because they're, if this is an example of how this is, then absolutely this is a fantastic series of talks. So thank you very much, and one more time applaud for Alex. All right.
Thanks a lot,
Thanks
Max.
so much. Thanks, everyone.
And thank you so much. I should pitch. I think Pratik's giving an upcoming talk, and I imagine he'll extend a lot of these things and really dive into some of the more, people are asking questions about ensembles and like isochoric, those different kind of processes and what they would mean for a machine learning system. And I suspect that's what Pratik will talk about. And I think it'll be a great talk. And yeah, thank you so much for inviting me. And I had a great time. And feel free to reach out if anyone has questions, or like I said, I think there's lots of questions to answer, and I think we could all work together to try to figure some of this stuff out. So thank you for the opportunity. Thank you.
Thanks a lot, Alex. Thanks, Max, for chairing the session. And I'll just make a quick announcement for the next week. We have Pratik, as Alex just mentioned, and we'll have Karthik from U Michigan as the session chair. So thanks everyone for tuning in. Thanks, Alex, for such a wonderful session, both in terms of the talk and the code walkthrough. Thanks, James, for your comments. Thanks everyone for the questions. So stay tuned. See you all next week.